Hi, you might know what is a function's derivative if we have only one independent variable. But what if we have multiple independent variables in a function? This is when partial derivatives come in the picture. So in this video, I will talk about partial derivatives and we will solve a concrete numerical example. So let's jump into it. Let's suppose we have a multivariate function f with n independent variables x1, x2, x3, xn. And in this case, we can talk about n derivatives because we have n independent variables. And these are called partial derivatives. These partial derivatives tell us how sensitive our function is with respect to each independent variable changes. So we will have the first derivative, df over dx1. We can denote it with f subscript x1, and also there is this mirror sixth symbol for partial derivatives. So this is the same notation. And this partial derivative will tell us how much our function value will change if we increase our x1 variable by epsilon, but our other variables will stay. So like this, and we will subtract the original value, because this way we will get the how much the function value changes, and we will divide it by little number epsilon. So this is, as you can see, the same formula as we've discussed in the previous video, but in this case we have more independent variables. And similarly, if we wanted to calculate the partial derivative with respect to x2, then we would do the same, but we would increase our x2 variable by epsilon. And so we would have these partial derivatives for all of the input independent variables, and for the last as well. So we would have this df over dxn partial derivative. So this would be with function value x1, x2, xn plus epsilon, and we would subtract, of course, the previous value with xn, and we would divide it by epsilon. And don't forget that all of these partial derivatives are functions. Let's look at a concrete example so that you would understand these better. So let's suppose we have a function f with three independent variables x, y, and z. And our function will be x times y squared plus z times cosine of z. So we will have three partial derivatives. The first will be this df over dx. This can be written as f subscript x, and we will use the previous formula we have written in this video. So we should put x plus epsilon in the place of x, and this way we would get this x plus epsilon times y squared plus z times cosine z, and we will subtract x y squared plus z times cosine of z, and we will divide it by epsilon. And let's see what we have here. So we have here xy squared plus epsilon times y squared plus z times cosine z, and minus xy squared and minus z times cosine z, and this is divided by epsilon. And here, as we can see, this z times cosine z eliminate each other, and also the x times y squared as well. And as you can see, we can also simplify our fraction by epsilon, so we will have this y squared. So our partial derivative of f of x with respect to x will be y squared. And let's continue. We will calculate the function derivative with respect to y. So that will be our partial derivative with respect to y, which can be written with this f subscript y. And this time we will put y plus epsilon in the place of epsilon. So x times y plus epsilon squared plus z times cosine z minus, and we have the original one with xy squared plus z times cosine z, and of course we divide by epsilon. And we have here a squared expression which can be written by y squared plus 2y epsilon plus epsilon squared. And yeah, we will just write out all the other expressions, but we will multiply by this negative one, so minus xy squared minus z times cosine z, and divided by epsilon. And we will use the fact that epsilon is much less than 1, so epsilon squared is very, very, very little number. I know this is not a right notation here, that it is approximately 0, but I mean under this that we won't calculate with epsilon squared, because that is much less than 1. So we will continue our calculation here. So as you can see here, we have this epsilon squared, which is much less than 1. So we have here xy squared plus 2xy epsilon plus z times cosine z minus xy squared minus z cosine z, and divided by epsilon. And here you can see that xy squared eliminate each other, and also the z cosine z. So after this we can simplify our expression by epsilon. So what we will get is 2x times y. So this is our partial derivative with respect to y. And the last is the partial derivative with respect to z. This is f subscript z. And this time we will put z plus epsilon in the place of z. And let me just write it a little bit differently, as I am writing this 1 over epsilon here, and we will do the calculation in parentheses here. So we have xy squared plus, don't forget to put z plus epsilon in the place of z. So this is multiplied by cosine of z plus epsilon, because here we also have a variable z. and we will subtract xy squared plus z times cosine z. So here you can see that we have cosine of z plus epsilon, and this I will write here what it can be approximated with. So cosine of z plus epsilon. We will here use the Ptolemy's identity, which tells us how to calculate cosine of a sum. And this is cosine of z times cosine of epsilon minus sine of z times sine of epsilon. And don't forget that our epsilon value is much less than 1. And this is why cosine of epsilon can be approximated with 1. And here we have sine of epsilon. And for this, I will write here the unit circle, because this will help us how to approximate this term. So here is our unit circle. And we have a very little angle epsilon here. So this is epsilon, and this sine of epsilon is this side of the right triangle, but this can be approximated with this part of the circle. And this part of the circle is simply epsilon, because our hypotenuse is 1. The important thing that you should notice and you should remember is that if epsilon is much less than 1, then sine of epsilon can be approximated by epsilon simply. And this is why cosine of z plus epsilon can be written as cosine of z times 1 minus epsilon times sine of z. So let's continue our calculation here. So we have 1 over epsilon times xy squared here, and we will do the multiplication here with writing cosine of z plus epsilon by cosine of z minus epsilon times sine of z. So we will have a plus z times cosine z minus epsilon z times sine of z. So here we multiplied this in the parentheses by z, and we have a plus epsilon times this, so plus epsilon times cosine of z minus epsilon squared times sine of z. And we have, of course, this negative before the parentheses, so we have minus y minus xy squared minus z times cosine of z. And I would like to highlight here that this term can be cancelled, because here we have an epsilon squared, and then that is much less than 1. And we will have some eliminations. So xy squared, for example, and z times cosine z, as you can see. So what we will have is epsilon times cosine z minus epsilon times z times sine of z over epsilon. And we will simplify by epsilon, and what we will have as a result is cosine of z minus z times sine of z. So this is our partial derivative with respect to z. So in this video we talked about partial derivatives and solved a concrete numerical example in which we had 3 independent variables, and we used only one formula for the partial derivatives. I hope you understood this, and we will meet in the next video.